nanoHUB-U, online instruction.
Welcome back. I'm Professor Rickus. In this lecture, we're going to take a look at a simple model of gene expression. So we'll look at a mathematical representation of both gene activation and repression. And then we'll look a little bit more closely at gene product production, and specifically hill function models and logic models. We'll also then look a little more closely at product decay and the steady state response and response time for turning genes on and off. So if we think about what the effect of transcription factor X on gene Y is, that effect could be either activation or repression. If X is an activator, it's going to increase the probability of transcription, often by increasing the probability of RNA polymerase binding upstream of our coding region of our gene. And if X is a repressor, then X is going to reduce the probability of transcription similarly. If we look at a network representation of this, we can represent each gene as a node, X and Y here, and we represent activation by a plus and or a straight arrow here. In the network view of repression, again, we've got our gene nodes X and Y, and we can represent repression with a blocked arrow here. And so looking at this, we can see if X, in this case for an activator, if the concentration or level of X is very high, then we would expect the expression of our gene, of levels of our gene X to be very high. We would expect the levels of our gene Y expression to be on. If our activation is 0, then our gene Y value expression levels would be off or low. And conversely, for X as a repressor, when X is high, the levels of X are high, then our gene expression for Y is off or low. And when X is 0, we have no repression, then our gene Y levels of expression are going to be on. So let's look at a simple deterministic model of gene expression. And just simply based on mass balance, if we look at the rate of change of Y, represented by dy dt here, where little y is our concentration of protein Y, gene product Y, inside the cell, then the rate of that change is going to be a sum of the rate of any transport of Y into the cell minus any transport of Y out of the cell, plus generation minus consumption. So in these cases, we're going to be focusing on generation and consumption. We're going to make the assumption and ignore that there's no transport of Y in and out of the cell. And so we're going to focus on generation and consumption, which can either be degradation or dilution from cell division. So let's look at this a little bit more closely. So now our rate equation simplifies now down to dy dt equals the rate of generation minus the rate of consumption. And again, we said generation here is, in our case, caused by gene expression. So the transcription and translation of that gene Y, right? So we can define a parameter beta, which is the basal or maximum expression in the fully on state. And the total generation rate is going to also depend on the level of our transcription factor that's acting either as a repressor or an activator. And remember, we said X modifies the probability of transcription. So then we can create a generation term now that is a product of our maximum or basal expression level beta times this probability of expression, which is a function of our transcription factor value X. So consumption comes from two major mechanisms, either degradation or dilution. Degradation can be passive or active. And this is a point just to sort of remind you that cells most often actively degrade their proteins through mechanisms such as ubiquitin proteasome. And so just to remind you and think of this active regulation event that's happening inside cells. And so alpha degradation, our rate constant, will be small if the protein is stable or not rapidly degraded, whereas alpha degradation parameter will be large for rapidly degraded proteins. Dilution now comes from cell dilution, or from cell division, where alpha dilution is essentially the growth rate of the cells. And every time the cell divides, it's going to split the protein that's originally in the mother cell into two daughter cells, thus diluting the protein concentration by half. So let's look a little bit more closely now at generation. And specifically, let's look at the Hill function model. So we said that our transcription factor X modulates the probability of transcription. So we need to put a function in here that represents how that probability varies with the level of X. And one very common function that works well for a lot of expression systems is this Hill function. And so the Hill function here, you can see is X, just to remind you, is the level of our activator in this case when we're looking at activation, the level of our transcription factor. So we have X raised to the power of N divided by X to the power of N plus this new parameter we're introducing, K to the power of N. And we'll see a little bit more clearly what K is in a minute. So if we then look at this function, and now we've normalized our transcription factor level relative to this K parameter. So I've just divided this whole thing by K raised to the N. And now we can plot this f of X. So now we've got a probability that's varying between 0 and 1 as a function of the concentration of our transcription factor relative to this K parameter in our Hill function. And we've got this plot for 4 different levels of our N, our Hill coefficient. And you can see in this for activation, this makes sense. When X values are low, our probability is 0. And as X levels increase, the probability of transcription and expression increases. Okay? This Hill coefficient N does a couple of things. It creates nonlinearity in this function, so we get this sigmoidal curve, right? It puts this curvature in here, this S shape into our Hill function. It also stretches out this function within the same range of X values so that you're more broadly spanning through this probability, getting closer to 1 from 0. Okay? And so this K value now becomes apparent. We can see that all of these lines cross each other, right? Where X equals K, X over K equals 1. And so from this, we can see now that K is the value of X, the concentration of X, where that probability f of X is 0.5. Or from a gene expression standpoint, where the expression level is half of the maximum possible value. And we'll come back to that in a second again. But let's first take a look at repressor version of our Hill function model. Very similarly, just kind of flipped here. So here we have our repressor Hill function, and here we have f of X equals 1 over 1 plus X over the K raised to the power of N. So here now we've already got our transcription factor level in this normalized form, normalized relative to our K parameter. And our plot looks very similar to our activator, just kind of turned upside down. So when we see when X is very small, then our probability of expression is high. And as X gets larger, then we see the probability of expression goes down. And K really defines that concentration range for when we say larger or smaller, how large, how small. And K really sets that value. Again, where K is the concentration of X, where X over K would equal 1, right? So the concentration of X, when it's equal to K, that f of X value is at 0.5, or we would be at half maximum expression. Okay, so just summarizing sort of what we went through here a second ago and looking at these two parameters we've introduced, our K value as well as our Hill coefficient. So K is in units concentration, and it really defines the functional concentration range of our value of X. Now it correlates, but is not formally, the binding affinity of X to our regulatory region in the DNA. There are other factors that can also contribute to this K value. And if we look at our function when K is very large, when X is very large relative to K, we can see our probability approaches 1. And therefore the rate when we multiply this by our beta, that rate then would approach beta, or our gene would be approaching maximally or at a high level of on state. When X is equal to K, when the concentration of our transcription factor, in this case our activator, is equal to our K parameter, again in units concentration, the probability equals 1/2, and our rate would be at half of that maximum level, or beta over 2. So our gene would be moderately on. And when X becomes very, very small, the probability goes to 0, and our rate would approach 0, and our gene expression would be off in this model. So to summarize again our Hill coefficient, as I said, the Hill coefficient increases the nonlinearity of this function, puts this curvature in it, gives it this sigmoidal shape, and it also increases the steepness of this slope in the middle range of where our transcription factor is functional. So the greater N, the more on or off switch-like our gene expression regulator system becomes. So let's look at that a little bit more closely. It's often useful to look in the extreme case. So if we look in the extreme of N approaching of infinity, then we become this switch-like on-off behavior. So here's a graph now of N very large, and we can see that f of x is near 0 for most of the range below K, until a concentration of our transcription factor approaches K, and as it gets very close to K, then our probability shoots up to be near or almost 1. And so now we have this switch-like behavior for that a broad range of concentrations of our activator, our system is off. And once it passes this K, which now is really functioning like a threshold value. So K is a threshold concentration. When X crosses that threshold, now our system switches on. Okay? And so our regulation of expression of Y is now switch-like. K becomes this threshold concentration. And one way to increase this N is by increasing the stoichiometry of binding. So N is, our Hill coefficient is related to, but again, not formally, the stoichiometry of binding of our transcription factor activator to our gene system. Quite often, there's quite a few transcription factor activators that act as dimers, so we'd have a stoichiometry of 2. And even up to 3, 4, and even 5 in some cases. So that's pretty common to have a stoichiometry greater than 1. And so if we look at this, and again, now if we go back to our Hill function, in the extreme case of N approaching 1, we can approximate our Hill function with a logic model, where theta now becomes a truth test of this statement, is X greater than K. If X is greater than K, then our theta becomes 1, or that statement is true, and our f of X is equal to 1, and our generation rate is beta, or our system is off. If X is smaller than K, then our test statement is false, theta equals 0, and generation rate is 0 or off. So as I said, note down here, in reality, N is very rarely greater than 4. 1 to 4, sometimes 5 is a very reasonable range, but very rarely greater than that. However, this logic model approximation is still useful, particularly when N is large, in dynamic analysis of large circuits, and also for building some intuition regarding circuit behavior, which we'll get to in following lectures after today. So let's go back to our governing rate equation for expression of our protein Y. So we have dy dt equals beta, our maximum expression rate, times the probability of expression, which is a function of our transcription activator, minus our decay of our protein Y, which has contributions from dilution or degradation. We'll simplify this for now. We're not going to look at the contribution of dilution relative to degradation. We'll get to this in a later lecture, and we'll just lump these together as the sum where alpha is our decay rate. So now when we plug in our Hill function for gene activation, we get this general rate equation now for gene activation using our Hill function model. So now we can ask, what are the dynamics of this system? And we're going to look specifically at the dynamics to turn the system on, where initially our system is off. That is, we have no transcription factor activator, it's at 0, and we also have no gene product Y to start with. And so then at some time, which we'll define as time equals 0, suddenly we have a large amount. What is large? Large is relative to our K. So we have a lot of activator relative to our threshold value instantaneously at time equals 0, and that stays on and is constant. Conversely, we'll look at the dynamics to turn off, where initially the system is fully on. We have a large amount of X. Again, large is relative to our threshold value at a constant. And at some time 0, we instantaneously turn our system off, and we take away that active X transcription factor there. And we can ask the questions, what is the steady state response? And we can ask the question, what is the response time to turn the system either on or off? So again, we've got our governing equation for simple activation up here using our Hill function model. And we're going to make a logic model approximation. So we're going to assume strong activation, that X is very large relative to K, and assume that f of X equals 1. And that simplifies our rate equation now to dy dt equals beta minus alpha Y. So we can solve for the steady state solution of this and see that our steady state level of our protein should be equal to about beta over alpha, okay? And so now if we look at this where our system is initially off, we have no expression, right? So Y starts at no expression, so Y levels are at 0, and we suddenly turn on at time equals 0. This gives us an initial condition of Y at time 0 equals 0. We can now solve for Y of t, and Y of t now equals beta over alpha, our steady state value, times 1 minus e raised to the minus alpha t. So this 1 minus e raised to the minus alpha t is now the dynamics, how quickly we get to that steady state value, right? So we go now looking at the trajectory of our Y value. We start at 0, and then at time equals 0, when the system turns on, Y starts to increase and approach our steady state value, which is beta over alpha. How quickly does it approach that? Well, that is determined by our 1 minus e raised to the minus alpha t. So this minus alpha now, this alpha, is really determining our dynamics of how quickly we approach our steady state value of beta over t. So if we define now and look at our response time, we'll define response time as the time it takes to reach halfway to our steady state value. Because remember, we can't look at the time it takes to reach steady state value. That mathematically would be infinite. Right? So we're going to define this response time as the time it takes to reach half the steady state value. Okay, so again, we have our Y of t equation that we solved for on the last slide. And now, now we can take a look, and if we plug in and say we can find the time t, which we now call t1/2, where Y equals the Y value at half steady state, which we know to be, we can define that as 1/2 beta over alpha. So we can now solve for that t1/2, and we see that t1/2 as we looked at in our function before, is dependent only on alpha, right? T1/2 equals natural log of 2 over alpha. So this is an interesting result, and perhaps not immediately intuitive if you didn't work through the mathematics, that the steady state expression level depends on both the expression strength, right, which would depend on things like how strong our promoter was in our gene design, as well as the decay rate, which is a product of both the dilution rate, the cell division rate, and the degradation rate, how quickly the cell actively degrades that protein. Whereas the response time depends on the decay rate. And we don't see that production rate, that beta, that would correspond, like I said, to the strength of our promoter, for example. And it only depends on alpha. So now we can sort of summarize this here, where we've got Y turning on. At time equals 1/2, we'll reach our 1/2, our steady state value, so that alpha determines how quickly we get there, and beta over alpha determine our steady state level of how high of a level that we get to. So now let's look at our off kinetics. We can do this very similarly. Again, we'll start with our simplified rate equation, dy dt equals beta minus alpha t. And we'll start with the system initially fully on. So initially we have lots of activator that's well above our threshold. At time equals 0, we instantaneously take that activation away. And if we start with our system fully on, then we'll start with our Y value at our steady state value. And at time equals 0, as expression turns off. So now, just as we did before, we can plug in our initial condition into our Y of t system, and at Y of 0, right, at our initial condition, our Y value equals steady state, we can again solve for T1/2 and the time it takes to get to 1/2 our steady state value. And T1/2 again equals natural log of 2 over alpha. So in both the cases of turning our system on and turning our system off, they both, how quickly those turning on and off happen depends on alpha by the same form, natural log of 2 over alpha. So we'll end this lecture today with a challenge. And your challenge or your homework is to work out the on and off kinetics for a repressor using the same approach. And 2, see if you can work out the on and off kinetics for an activator as we did today, but this time without making the logistic approximation of the Hill function. And ask yourself, does it make much of a difference, either qualitatively or quantitatively? So this is sort of testing ourselves against this. Is this approximation that we made fair, and is it useful? So you'll need to do some numerical integration, such as in using MATLAB or another similar tool to do this. And if you vary n, k, beta, and alpha, watch to see how your curves change of your protein product Y versus time. And it's good to build some experience and intuition about how the time course and the final levels of expression are going to vary with these different parameters. So next up, we'll take a closer look at gene product consumption rate alpha. And we'll look at this particularly in real cells as well and ask what's the real half-life of proteins in cells. And we'll also start looking at dynamics when we put together activators and repressors to make some simple circuits. Hope to see you next time.